Thanks for the introduction. So today I'm going to present a work which was done by Pedro Ciambra during his master and is now starting in his PhD, but he couldn't come here. So, and I will talk about co-optimizing Dataflow graph factors with MLIR. So just a bit of context to know what I'm talking about. Come on. Okay. So Dataflow is what we are trying to do today is bringing together two areas of research. On one part, Dataflow, it's a programming paradigm for parallel applications, popular in the field of signal processing, but suffered lacks of interoperability between different compilers. It was already presented yesterday. It's something that we are, I guess, used to. I'll just give you a short introduction afterwards. And something that you may not all know is the MLIR project, which is focused on compatibility and reuse. It is part of LLVM. That's a mainstream compiler framework. You know it maybe from Clang, one of the two main compiler which is used today for general purpose systems. And the goal of MLIR project is to allow for quick development of domain-specific compilers. And what we want to do is bridge the gap between Dataflow research and compiler framework by proving that we can do a Dataflow compiler that uses the MLIR framework as a support, and to the demonstration what this new compiler could bring is better integration between high and low level optimizations. So a bit of background about what I talk. So first, Dataflow programming paradigm. We are going to model the algorithm as a directed graph, as shown yesterday. We got vertices, which are actor, which are combination units that acts on tokens of data. And the implementation of an actor is called a kernel. I may use one or the other. And the edges are FIFO data structures models. And we can see here, we got just an application which exchanges data between different actors. And what is really interesting is that we got a different level of parallelism and explicit data exchange, which helps optimizing the Dataflow graph, which has been something that's been done for quite a few years already in Dataflow. And then the LLVM compiler framework. If you wonder where was Clang, Clang is right at the top here. And one main feature of the LLVM, which was really a game changer at the time when it was released, the LLVM IR, which is a level of abstraction between C and assembly. And it's the same level of IR, which is used for all different languages and all different hardware platform, which helps to share optimization and brings good improvement in compiler research these last few years in compiler performance. But there is a demand for further flexibility. Each language that you've seen for the C, Rust, or Swift are using different high-level IRs between LLVM, and many of these languages have similar features encoded in their IR. Basically, they are similar, but they don't share all that part, all the upper level part. So MLIR is trying to answer that problem. It's by raising similar abstraction across different compilers. So it's a framework for the definition of modular IRs. It was made with machine learning and accelerator in mind, and the MLIR, and was originally part of TensorFlow, pushed a lot by Google. And we're going to start with different languages like C, C++, Fortran, TensorFlow, etc. We got this big box MLIR, and the promise is that you're going to be able to compile to all of these different languages. And how it's done is done by bringing various different dialects, which are going to provide different abstraction, and each of those abstraction will help you optimize the graph in the right way. For example, we can see from the C, we can go to structure control flow graph or an affine representation, and then we are going to specialize to go through LLVM to go to the classic processor, but we could also go to GPUs here with CUDA or the ROCm for MD, but we can also do kind of HLS, go to VHDL with circuit, etc., etc. So there are various different dialects, and they implemented transformation from one dialect to another to be able to lower from this high-level language to those platform by sharing also those dialects and the transform on those dialects. And our project Yara is going to build on this MLIR framework. Also, Yara is an MLIR-based Dataflow compiler. Is going to define a new dialect for Dataflow because it's a different representation from what is present there. It's going to represent edges, actors, ports, parameters, subgraph, etc. And we're going to provide a the proof that MLIR is providing new value is by providing co-optimization infrastructure to change the graph and the kernel code concurrently. This is not something that was done up to now, or very difficult, because it was separated between the Dataflow compiler on one part and the kernel code compiler on the other part, and that allows for novel early dead code elimination path. So that's a proof that I'm going to detail. And to prove that it works, we're going to generate a very simple single core SDF schedule for Dataflow graph. And it's going to be just a function with sequence of kernel codes and memory offset to prove that we are able to generate code and this compiler works for simple application. So my Yara compiler flow starts with both the kernel in C code and the graph in diff. So that's a Dataflow interchange format represents our Dataflow graph. First thing that we're going to do is parse this diff, which is existing, and get our Yara dialects with the built-in dialects, translate this graph to the internal dialects. So yeah, the Yara dialect is a high-level topology dialect. It's structurally similar to diff, so a representation of Dataflow graph with name actors, ports, and graph, and with reference to actor implementation, kernels on other graph. So we got an example here. We have an actor, which is a read RGB frame N1 with one output port, which is a char, an array of char value, RGB values. And we're going to represent that with this format, which is an internal format, the internal dialects, which are going to define all the parameters, the output, the type, the number of value which are exchanged, the name of the actors, and then we're going to implement that. Basically, we have here we can find a function, and now it's the node, the actor is a call to this function, so an instantiation, and we're going also to represent all the edges between the different actors, etc., etc. So compilers is going to have access to all those information. Then we're going to provide reuse the C frontend from MLIR, which is built on top of Polygeist, an existing piece of software, and we're going to have both the graph and the kernel with Yara dialect and built-in dialects for the C code. And now we are able to perform our co-optimization because we've got those two dialects in the same compiler, and we're going to try to do dead code elimination, which was not something that was easy to do at that level. So here's an example. We are going to automatically remove the operations that accessed only unused output. So that's the dead code elimination. We don't use some value. So in this example, we got a Cartesian to polar transformation starting from the XY coordinates and computing the R and theta. So that's a generic function. We compute both values, but you may want to use only one of those values. In this example, we want to use only the theta value. We don't need to have the radius, only the angle. And what we can see is that we got a bunch of instructions here which are completely unused. And what we're going to do is remove those instructions. We couldn't do that before because the output of the Dataflow graph was always used, and we couldn't remove used value. But now, because we master both the graph and the code inside the graph, we are able to remove the value outside the graph, and we are able to remove at the same time the code inside the graph and do this multi-level dead code elimination in a maybe a simple optimization, which we were not able to perform before because we were not sharing all those together. And then we're going to do scheduling and bufferization. So those are classic optimization that we had to implement from the Dataflow community. And we didn't invent anything new here. We have a greedy scheduling algorithm, which fire any actors that has enough token in its input FIFOs. And we just have a priority on firing the same actor sequentially to improve memory locality. And this is, non-work from Grammarian NL, 15 years old. And we are also using memory pool-based bufferization. So we use memory after tokens are consumed. It's a first fit strategy. We grow pool if no contiguous space is found. So that's another classic implementation, which is one which is currently used in Prism, which was presented yesterday and developed by Carol here and other colleagues at IETR. And we just re-implemented this optimization here. And all of that fit in our system. So we're starting with the C, C++ language. We're going to add the Dataflow as an diff as an input. And we're going to add our Yara dialects here. And we're going to have a transform some diff to the Yara. And then we're going to transform to a structured control flow. When we have scheduled and bufferized the graph, it's going to be just sequential C code. And based on that, we are able to reuse all the classic LLVM compiler chain and integrating the C++ here as well. And as a result, we got several experiments to prove our system. So those are developed from publicly available application developed by the Prism team. Experiments are run on a simple Linux desktop with, we merge the wartime memory usage with GNU time and compile with C-Lang LLVM, indeed, used in MLIR with O3. So first example is more of a new application specifically to prove our system. We got only 4 nodes, 3 edge and 4 kernels. So a very small application. We're going to take the input, read the RGB value, transform that to HSL, which is hue, saturation, and luminance, so another format for the colors, and then only read the luminance, so that's going to be some kind of black and white image, and then transform that back to RGB to display it. And in Prism, we do not have support for unused output, so the Prism implementation is going to write into a global buffer, but in our case, we are able to remove those output with the date code elimination that I just presented. And what we can see is that the memory usage between Prism and Yara is already better in some way in memory usage, but similar in terms of execution time. In terms of memory usage, when we apply our date code elimination, we got yet another improvement because we are able to remove that part. And this brings an improvement in execution time even for a simple compiler. Then we add additional application which does not display date code elimination optimization. There was no opportunity, but from simple application like Sobol filter, we are able to compile and execute about the same time, -1% for one or the other, but really same performance. And we are able to perform small application, but also larger application like swimmer detection or SIFT application, which is composed of many different kernels. And here we can see that our compiler is still early stage because we are consuming much more memory, especially in the last case where there is a lot of data copy which is encoded in the graph and we are not able to optimize, which means that sometimes we can have better execution time, but due to this additional memory usage, we're going to have worse execution time on larger application. But still, our compiler works for generic large application, which is already a very good step. So in conclusion, we've provided the first functional optimizing compiler for Dataflow. To our knowledge, this is the first work that joined C and SDF compilation, so the Dataflows that we're interested in. What is very noteworthy, it was developed in a 1-person year, thanks to MLIR, going from scratch to a full compiler working for a single core with new optimization. It already works with multiple existing applications, as we've shown, and this is still single core and needs works on performance. We've demonstrated novel optimization for Dataflow. So the data elimination is the first step. We will plan to do many more. And we got many potential future research direction. So the polygaze that we use only as a front end also provide a lot of procedural optimization, which could be mixed with Dataflow, would be interesting. And we could support for the operation of different MLIR dialects, because now we're sitting in MLIR, so we don't have to restrict ourselves to C code. We could even get directly machine learning dialects like TensorFlow, integrate that inside our system. And definitely we are working in, this is a single core, we are targeting multi-core optimization and maybe even heterogeneous system. And that's all for me. Thank you for your attention, and I'm ready for your question.
Okay, I've got at least one. I don't know very well MLIR, but I was wondering if you've got a way in the dialect to describe the architecture at some point. Is there something already existing, or are you able to add this in the dialect?
That's an interesting question. I don't know all of MLIR to know if it's present, but definitely that's something that we have to start. Right now we're imposing single core, so we don't really have a model for the architecture, but if you want to go to multi-core heterogeneous system, which is way to go today in terms of architecture, that is something that we'll have to look, and maybe we could just have another dialect to represent that in some ways. Yes, that is definitely an area of research that we want to look at.